Hello everyone, today we're going to learn about alloys. An alloy is a homogeneous mixture of metals. Another way that you might define this is it is a solution of metals. The additional metal atoms that are being placed into it are going to either substitute into the existing crystal lattice or will go into the spaces in between. This results in us having two different types of alloys that we will discuss a little bit more. If the metal atoms are substituting in for an atom of the main metal, the solvent if you will, you have a substitutional alloy. The two metal atoms must have similar radii for a substitutional alloy. That way, the lengths and therefore the strengths of the bonds are similar in a substitutional alloy. If the atom that's being added is going into the space in between, it is an interstitial alloy. The metal that is going in must be significantly smaller compared to the metal that it is going into so that it can fit in that in-between space without stretching the bonds unreasonably. You should be able to predict what type of alloy two metals should form based on where they are located on the periodic table and what you know about atomic radii trends. So let's make some predictions about the following pairs. Let's look at zinc and copper, manganese and boron, aluminum and silicon, mercury and potassium, and platinum and lithium. Zinc and copper are very close to each other on the periodic table and therefore have very similar atomic radii. Therefore, they are most likely to form a substitutional alloy. Manganese and boron, on the other hand, are quite far away from each other on the periodic table and have very different radii. Therefore, it is more likely that they will form an interstitial alloy, with boron going into the space in between the manganese ions. Aluminum and silicon are very similar in size since they are near each other on the periodic table. Therefore, they're most likely to form a substitutional alloy. Mercury and potassium, as well as platinum and lithium, both have large differences in radii because they are far away from each other on the periodic table. Therefore, both of these pairs will form interstitial alloys. You should also be able to make some predictions regarding properties for an alloy based on what kind of alloy is formed. Specifically, we will focus on density and melting points. With regards to density, a substitutional alloy has a similar number of particles with similar masses within a space. Therefore, they should have some densities that are very similar to the original densities of the metals that make them up. An interstitial alloy, on the other hand, has additional particles that have been forced into the space, in those in-between spaces. They often end up with higher densities. Some interstitial alloys, though, will have smaller densities, specifically if the particle that is put in the in-between space is large enough that it will stretch the bonds of the crystal lattice, therefore resulting in overall less particles and less mass occupying a space. Or conversely, you could think of it as the mass requires a larger space to be present. For melting points, substitutional alloys have similar numbers of bonds with similar lengths and strengths, and therefore they are likely to have very similar melting points to their original counterparts. Interstitial alloys, on the other hand, have additional particles within the space and therefore have additional bonds and interactions, meaning that more bonds must be broken before they can melt, and therefore they will most likely have higher melting points. While there are always exceptions to both of these patterns, these are things that are generally going to be useful to rely on when determining what the properties of an alloy might be.